Hello, this video is on potential energy diagrams. Before we get into the actual questions on the nitty-gritty of potential energy diagrams, first wanted to talk about the kinetic molecular theory. Kinetic molecular theory states that molecules are always in motion, so it explains the forces between molecules and energy that they possess. So when molecules are always in motion, there's three different states. There's solid, liquid, gas. Solids are vibrating, liquids are sliding past each other, and gases are floating around, bouncing in any which direction. Collision theory states that if molecules are always in motion, then they're going to be bumping into each other. So in order for a reaction to occur, collisions need to occur. And that is when an activated complex is formed. What's an activated complex? It is the temporary intermediate between the reactants and the product. So when you have two reactants come together, they're going to collide and form this activated complex. And then they're going to split apart and either reform into the reactants or into the products. All right, we've got two potential energy diagrams right here. First one on the top. This is an exothermic reaction because our reactants are starting with lots of energy and our products are ending with less energy. The difference is the energy lost, or the change in enthalpy, the delta H. And since we're losing energy, our delta H is negative. It's exothermic. So if this reaction is happening in a beaker and we're holding that beaker is going to feel warm because energy is going into our hand. The next one right here, this is an endothermic potential energy diagram. We start with little energy and we end with a lot more. So we're gaining energy, it's absorbing energy, it's endothermic, it's a positive delta H. If that reaction was occurring in a beaker, it would feel cold because it is absorbing energy from our hand, giving the feeling of cold. All right, activation energy is the energy required for the reaction to occur. So it's not just going to, most reactions will not occur just spontaneously. You need to input just a little bit of energy, whether it be exothermic, like the reaction on the right, or endothermic, like the reaction on the left. It needs energy to be inputted. Endothermic is going to require a very much larger activation energy, whereas exothermic doesn't require as high of an activation energy. All right, now let's get to potential energy diagram and labeling all of the things that could be labeled. So this first thing that could be labeled, well, first of all, is the reaction endothermic or exothermic? So if I start with more energy and end with less, I'm giving off energy. Anytime I give off energy, I'm exothermic. All right, what letter represents the potential energy of the reactants? All right, potential energy of the reactants. These are my reactants, and I have all of this energy. So that would be B is the potential energy of my reactants. All right, next question is, what letter represents the potential energy of the products? So these are my products. This is my potential energy, the total amount. So that's F. Next one, what letter represents the heat of reaction, which is the delta H, the change in enthalpy of reactants to products. So here's my reactants, here's my products. Looks like D is that change in reactants and products, the energy, so D. Next one, number 5, what letter represents the activation energy of the forward reaction? Right, activation energy of the forward reaction is going this way. We're starting here and we need to input this much energy, so that would be A. Let's see, activation energy of the forward reaction. How about the reverse reaction? That's going this way. So we need to input all of this. It's going to be E, product potential energy, and then here's the activation energy required, E. Next one, number 7. What letter represents the potential energy of the activated complex? Now the activated complex is this guy right here, and that would be C. So you need to start with your reactants, potential energy. You have to add a little bit more energy to form that activated complex. It's then going to either reform the reactants or release all of this energy while forming the products. So that is C, is the potential energy of the activation complex. Next is a reverse reaction, endothermic or exothermic. So that's going this way. So we start with less energy, end with more. We absorbed, so it's positive delta H. It is definitely endothermic. And then the last question on this sheet is, if a catalyst were added, what letters would change? So what is a catalyst? Catalyst is an entity that speeds up the reaction and is not consumed in the reaction. It kind of just facilitates. So it's not necessarily a reactant, it's not a product. Alright, so how does it speed up a reaction? What it does is it lowers the activation energy. So instead of having this activation energy, now you may only have this activation energy. So all of the excess energy now can go towards forming more activated complexes. Alright, so what letters would change? Well, it looks like C, the potential energy of the activated complex, would definitely change. A, the actual activation energy changes. And it looks like E, the activation energy of the reverse reaction would also change. Alright, now we're going to flip this page over, and there's some really slick questions that hopefully will ingrain this concept of potentially energy diagrams down. First question is the reaction exothermic or endothermic? So lots of energy, not much energy, so we released energy. That's going to be exothermic. I'm going to just put exo for short. What is the delta H? Value of delta H. So that's change in energy of reactants to products. And I'm going to do final minus initial. So that's 10 minus 40. 10 minus 40 gives me negative 30. And we're talking about kilocal, so it's negative 30 kilocal. Alright. Next, what is the value of the activation energy of the reaction? What is the value of the activation energy of the reaction? So, activation energy is from our reactants to our activated complex. So it looks like our final minus initial is 16 minus 40. 16 minus 40, which is 20 kilocalories. Next question, what is the potential energy of the products? Right, there are products, potential energy looks like is 10 kilocal. And last but not least, what is the potential energy of the activated complex? That's this guy up here, looks like it's 60. That is question 1 through 5. Alright, now trying questions 6 through 10 out. Let's look at these guys. Number 6, is the reaction exothermic or endothermic? Little energy in the reactants, a lot of energy in the products. Looks like we're absorbing energy. This is going to be endo. So endo for endothermic. 7, what is the value of the activation energy of the uncatalyzed reaction? So here's catalyzed reaction, and here's uncatalyzed reaction. We're looking for the value of the activation energy. So that's going from our reactants to our activated complex. Looks like 20, 25, 30. Looks like that's 35. What is the value of the activation energy of the uncatalyzed reaction? That's 35 minus 10. That's 25. And looks like the Xerox wasn't being friendly. I'm just going to assume that's in kilocalories. Alright, number 8. What is the value of the activation energy of the catalyzed reaction? Alright, so we're going from our reactants to our activated complex of the catalyzed reaction, which is now 30 minus 10. 30 minus 10 is 20 kilocalories. Number 9, what is the potential energy of the activated complex of the catalyzed reaction? Potential energy of the activated, so that's of the catalyzed reaction, that's this guy, so that's 30 kilocalories. And number 10, how does delta H for the catalyzed reaction compare to delta H for the uncatalyzed reaction? So we're just comparing these differences, but we're looking for the delta H. So that's just the difference between the reactants and the products, which is going to be 25 minus 10, 15. That's not going to change whether it's catalyzed or uncatalyzed. So we're going to write no change. Alright, we're going to be going on to our last set of questions. Number 12, activation energy of the forward catalyzed reaction. So that's forward catalyzed reaction. So we're going from here to here, the activation energy. So trying to find, looks like E is our best bet in that case. Oh, looks like I started with 12. How about looking at 11? It says potential energy of the activated complex for the uncatalyzed reaction. That's looking like here. So that's going to be our H. Alright. Now we're going on to 13. Potential energy of the products of the forward reaction. Here's our products. It goes all the way to, it looks like B would be our correct answer for that one. 14. Activation energy of the uncatalyzed reverse reaction. So now we're going here, reverse reaction, and it's the activation energy. So we're going from here to here. Trying to find the arrow that matches that. Looks like G matches that spot on. And then we got 15. Potential energy of the activated complex for the catalyzed reaction. And that's going to be this guy. Goes up to there. Looks like I. It's our best bet. Number 16 is activation energy of the uncatalyzed forward reaction. Activation energy, so that's here to here. And it looks like F would be correct for that. Number 17, the heat of reaction, delta H. So we're going from reactants to products. Looks like A would be good for that. Number 18, we have activation energy of the catalyzed reverse reaction. Activation energy for that guy. I'm going to go with C. Potential energy of the reactants for the forward reaction. Looks like this guy, which is D. And that is how you understand potential energy diagrams. Thanks for watching.